Have you ever wondered how a machine learns to play a super complex game like Go or chess, and not just play it well, but better than any human on the entire planet? It's not like it's memorizing every possible move. Nope. Instead, it learns through this incredible process of trial and error. And today, we're diving headfirst into exactly that, the world of reinforcement learning.
All right, so here's the game plan. We're going to start with this quest for a totally new kind of learning. Then we'll build a simple little world with some clear rules. But then we're going to see how that whole approach shatters when things get really complicated. And that's when our hero, the neural network, swoops in to save the day. And finally, we'll look at how we actually train an agent to become truly intelligent.
So, first up, the quest for learning. What exactly makes this way of teaching a machine so different from everything else out there?
Okay, this right here is the absolute key difference. You know, most machine learning you hear about is predictive. You basically hand it a giant textbook, like millions of cat photos, and it studies and studies until it learns what a cat looks like. Reinforcement learning? Totally different. It gets no textbook. It's more like we drop it into a maze with no map, and it has to figure everything out on its own. It literally creates its own data by just trying stuff. In this little explorer we're talking about, it's called the agent. The best way to think about it is like a brand new character in a video game. It has no clue what the rules are, what's good, what's bad. It just has to start moving around, taking actions, and learning from the points it racks up, the rewards, and, the points it loses from the punishments.
Okay, so to really get how an agent learns, let's build it a little playground. We'll head into our second section here and actually define the rules of its world.
Welcome to the grid world. It's a super simple game, but trust me, it has all the pieces we need. Any square our agent can land on, that's a state. The moves it can make, up, down, left, right, those are its actions. Then you've got special squares, like a treasure chest or a trap, that end the game. We call those terminal states. And the goal? Well, that's easy. Find the path that racks up the highest score.
So here's the crucial idea. How does the agent decide where to go? It learns to figure out the value of every single square on the board. And the value isn't just about the points you get for landing there right now. No, it's the total potential score you could get if you started on that square and played a perfect game from that point on. The agent's whole job is to build a mental map of these values.
And it figures out those values using something called the Bellman equation. Now, I know it sounds super complicated, but the logic is actually really simple. To figure out the value of where you are, you just peek at all the squares next to you, find the one that has the highest known value, and boom, that becomes your new potential. It's like working backward from the prize.
And we can make our agent even smarter with a little twist. What if we say every single step it takes costs a tiny bit of energy, like a minus 0.1 point penalty for each move? All of a sudden, the agent isn't just looking for the prize anymore. It's trying to find the fastest path to the prize, because just wandering around is now costing it points. This makes it way more efficient.
Okay, so our little grid world method seems perfect, right? The agent can just figure out the value of every square and find the best path. Easy. But what happens when the world isn't a tiny 5x5 grid? Well, this brings us to the huge critical flaw in our plan.
Just look at this number. This is the number of possible board positions in the game of Go. That's a 1 with 170 zeros after it. And that isn't just a big number. It's a number so big our brains can't really even process it.
To put that into perspective, it's more than the number of atoms in the entire known universe. So our simple idea of visiting every state and giving it a value, the whole thing just completely falls apart. You can't draw a map when the territory you're trying to map is literally bigger than the universe itself. It's just impossible.
Which, of course, leads us to the big, flashing question. If an agent can't possibly map out the whole world, how in the world can it learn to make good decisions? How do you navigate a world that's just too big to even comprehend?
And this, my friends, is where our hero enters the story. Let's jump into section 4, because this is where a neural network comes in to solve this impossible problem by basically throwing out the old rulebook.
You see, the magic of a neural network is that it can generalize. It doesn't need to visit every single square on the board. Instead, after it's seen just a handful of them, it starts to get a feel for the pattern. It starts to understand that, hey, this spot is valuable, so the spots near it are probably pretty valuable too. It learns the general shape of the landscape, which lets it make a really good guess about places it's never even been.
And we can use this neural network in two main ways. First, there's the value network. It's kind of like our old system, but on steroids. It just asks, how good is this spot I'm on right now? But then there's a more direct way, the policy network. It completely skips worrying about the score and just answers the question, okay, what's the best thing for me to do right here, right now?
So let's stick with that policy network, because it's pretty cool. How does it actually learn the right moves to make out of thin air? This brings us to our final section, how we train a truly smart agent.
Well, the training process is actually pretty intuitive. First, the agent just plays a whole game using whatever random strategy it has at the moment. Let's say it wins. The network then looks back at every single move it made along that winning path and basically says, okay, all of those were good moves. Let's make it more likely we do those again. And if it lost, it does the exact opposite. It discourages those moves. You just repeat that feedback loop millions of times, and out of all that randomness, a brilliant strategy starts to take shape.
But there's one last crucial piece to the puzzle. The agent is always facing this dilemma. Should it exploit, use the strategy that it already knows works to get a pretty good score? Or should it explore, try a totally random move that might be a disaster, but might also lead to a brand new genius strategy? The best agents do both. They mostly exploit, but they always leave a small chance open to explore, making sure they never stop getting better.
And that really brings us to the end of our journey. We've seen how an agent can start with absolutely nothing, no data, no instructions, and through pure self-play and correction, learn to master these incredibly complex worlds. So it leaves us with this one last huge question. If this method can conquer games, what other giant real-world problems in robotics or medicine or designing new materials are they going to solve next? What happens when we finally unleash this quest for learning on our own world?